Well, good afternoon, and today actually we're going to carry on looking at transformers. So I think last week we had a look at types of transformer and ideal transformers, and some electromagnetics related to how transformers work, and also some of the limits in transformer operation in terms of the magnetic saturation and the coil temperature. So in this particular part of the lecture, we're going to look at the equivalent circuit, how we get the equivalent circuit, and what it means, why we need it. So if we look at a practical transformer that we would want to use in real life, in a power system, then it's not 100% efficient because we have losses and leakages which are more than zero. So we have to consider them in some way, and this is really what we're going to sort of look at in this first part of the lecture. So there's input current, which is greater than zero when the secondary is open circuit. So in other words, if we don't have any current here, there is still current that's going to flow here. So this causes a certain amount of loss. Anyway, what we're going to do really is we're going to look at these things here, and these things here, because these represent a real practical transformer which has losses. So the first we're going to do is look at winding resistance. So as you know, as we've discussed, we have copper wires which make up the primary and secondary windings of our transformer, and those windings, this copper material is not a perfect conductor, so because of that we represent these resistances to take into account the fact that our copper wires have some resistive loss. So we have RP on the primary side and RS on the secondary side. So of course, what we can do now, if we know this, we can calculate a power loss. So what that really means is that we can no longer achieve this 100% efficiency, okay? Because some of our power is going to be lost in these two resistors. So in a practical transformer, then we have a finite permeability. So what does that mean? So what that means, you see, is that the permeability, the magnetic permeability, is equal to the magnetic flux density divided by the magnetic field H. And this magnetic field H is generated from a current. So for example, we have a voltage source here and a primary current, and that primary current sets up a flux, and that flux density is shown by this current, can be found from this BH curve, and that's a finite value. So you need a current to establish the flux in the core, and because that's associated with a magnetic component, then we use an inductor to represent that magnetic flux being set up by that current. So one important thing here is that this magnetizing current IM will flow even when the secondary windings are open circuit. So in other words, if we have no load here, so we have an open circuit or infinite impedance across this secondary, we're still going to have this magnetizing current. So for practical transformers, the reluctance of the core is going to be greater than 0. So we can write down this equation here, that the magnetic motive force of the primary is equal to magnetic motive force of the secondary plus the flux times the reluctance of the core. Okay, and then we can add that on to the secondary consideration. So normally, actually, if I do this would be from our perfect transformer equation, but in a practical transformer we have to add on that flux times the reluctance of the core term on the right hand side. So number turns primary times the primary current is equal to the number turns secondary times secondary current plus this term here. So we can solve this for flux, and we can solve that in terms of the magnetizing current. So then we can rearranging this equation here, we can see that magnetizing current is equal to flux times the reluctance of the core divided by the number of primary turns. And having done that, we can now calculate the inductance for that related to that magnetizing current. So we know the number of turns in the primary and the flux, and we divide that by the magnetizing current, and we end up with the number of turns in the primary squared divided by the reluctance of the core will give us the value of magnetizing inductance. So you see, this is a finite value, whereas in an ideal transformer that'll be infinity. And we can multiply this by the angular frequency to get the inductive reactance, and so we just put an omega in front of that term there. But what this all this really says is that we have finite values in a practical transformer for that inductance and reactance. So that's basically what the effect of the magnetizing current is. You end up with finite values for the inductance and reactance in that equivalent circuit. So the third thing we have to look at then to get these equivalent circuit is the leakage inductance. So what we're considering in an ideal transformer is that the flux is confined to the iron core, but in practice around the windings there is some flux due to leakage inductance. So there's some flux which is not in the magnetic material, in the iron material. So we need some inductive term that helps us describe this phenomenon, and that occurs both in the primary winding and in the secondary winding. So that's why you have on both the primary side and the secondary side, because these are set up by the currents in each winding. and they are in series with the winding resistance. Okay, so if you consider the windings themselves, effectively they're a series RL circuit. So normally this is actually minimized in practical transformers by interleaving the primary and secondary windings. And the last practical factor in generating this equivalent circuit is iron loss. And there's additional losses associated with the core, and we group them and we call them iron losses. And there are two components to this iron loss. One is eddy currents, and one is hysteresis loss. So we're going to look in detail actually at hysteresis loss in the next part of this lecture. And we're not going to cover eddy currents in the lectures, but if you look on the wiki, you should see there should be a page which explains eddy currents. And the thing about these particular two things is that they are real power loss, and so because they're real power loss, they can be modelled as a resistor. Okay, so again we'll cover hysteresis loss in detail. Eddy currents is on the wiki. There's a wiki page for eddy currents. Please read that to make sure you know what eddy currents are, and we'll have some example questions and example classes which cover that, but which I think will be better actually than going through their lecture. It's more easier to see an example. So we'll do that in a couple of weeks' time. But the next part of the lecture we'll look in detail what we mean by hysteresis loss. Anyway, so now we see we have all these components. So remember the iron loss, as we'll see actually, we'll look at hysteresis loss, generates heat loss, so it's real power, so it's a resistor. So actually, when we look at these losses, there are ways of minimizing them, and again, this is described in the wiki why we use laminations to reduce eddy currents, and we'll look in much more detail actually at hysteresis loss. Okay. So now we have an equivalent circuit for a practical transformer. So we have the primary side and we have the secondary side, and the thing to note is that on the primary side we also have this magnetizing current and we have the iron core losses. And this circuit still has an ideal transformer connecting the primary and secondary sides. So what we want to do is we want to eliminate that ideal transformer. And this makes the analysis a little bit easier in practice. And we do that by doing something called refer to primary side. So let's consider if we just have this ideal transformer and we have a impedance as a load. So we can say that Z2 is equal to V2 over I2. But from our transformer equation, we know that V1 over V2 is equal to N1 over N2, and I1 over I2 is equal to N2 over N1. So we can substitute V2 and I2, and if you do the substitution, we can get that Z2 is equal to N2 over N1 squared times V1 over I1. So what we can do then is we can replace all this with this, because we can call this here Z1, and we can say then that Z1 is equal to Z2 over N1 over N2 squared. So what that does is it moves this impedance here on the secondary side over to the primary side. And this Z1 is basically Z2 that's been moved to the primary side. So using this principle, we can move all the components on the secondary side onto the primary side. So we lump all those elements together and call it Z2, and we can move them over to the primary side. And so using that, using the turns ratio squared, we can move all these components over to the primary side and generate a simple equivalent circuit without a transformer. And of course we can lump the resistive elements together, and we can lump the inductive elements together. So this is our final equivalent circuit. Okay, so here's an example actually which you can try for homework. In fact, I put the slides onto Moodle, and the solution will be on the next slide, but please, when you work through it, try it first before you look at the solution. If anybody has any problems, I'm quite happy to go through the solution in a lecture. So we probably will anyway, actually, go through the detailed solution, okay? But you'll see on the next slide that there are some answers really, with some working. It's not that detailed, in fact, but yeah. But please try that as homework, and we can go through that if people are unclear where these answers come from. If anyone has any questions, then please, let the GTA know or let me know somehow, and I can try and answer them. Otherwise, I think this concludes this part of the lecture.